Thank you for coming. I will not be offended if you won't listen to this talk and work on the workshop itself. So feel free to start hacking. Okay, a little bit about me. So I've been doing NLP for a while now. I've been doing NLP at Yahoo Mail, at AT&T. Microsoft did some machine learning. Currently, I'm leading the data science for Best Practice. In Best Practice, we basically do NLP on legal contracts. And all of the examples that you're going to see today are legal documents from this reason. Okay, this is our agenda for today. First, we're going to talk about NLP in general. Then we'll dig into word vectors and why are they useful. Then we'll talk about neural networks. That will be the subject of this workshop. And finally, we'll talk about our data set, Google Colab, configuration, and how to get things actually working. I remind you all that this is a prize-winning competition. So code as long as you have to, and submit. The best model will be awarded. What are the best 3 prizes? Never mind, Leo will share with you later. Okay, so NLP, like most machine learning fields, can be divided into supervised learning and unsupervised learning. Unsupervised learnings are mainly tasks like clustering, topic modeling, in which I have a lot of documents. And I don't know what they're about, but I want to cluster them together. It's pretty useful in information context, military context, also to identify languages, slangs. Another pretty common unsupervised task is text generation. I have a chatbot and I want to generate an answer. Anyone have heard about the GMT2 fiasco, generating fake news? So fake news is another example of text generation in a supervised way. We will be focusing on supervised learning. Anyone here has been to the previous workshop on classification? Okay, so not a lot. The common supervised tasks are classification, named entity recognition, which will be the subject of this talk, sentiment analysis, and machine translation can be seen as either supervised or unsupervised, because there's more than one way to translate a sentence. It depends who you ask. So, a brief overview of supervised NLP tasks. The first one, and by far the most common one, is text classification, in which I have a lot of documents. I've trained some kind of model, and the model needs to predict what class is the document. It's really important to note that I know all of the possible classes in advance. This is not unsupervised. I have someone who labeled the data, and I know the ground truth for each document. For those who are interested in text classification, you should follow this link for a previous text classification workshop, in which we classify legal documents, what a surprise, into their contract type. This is an example data point. We have this agreement, and we need to classify it into one of those 6 types. I think there's also videos available for the previous workshop. In either way, follow these 2 links for more details. Sentiment analysis, another very important supervised learning task. One might think of sentiment analysis as a special case of classification, because I have 3 classes, whether the sentiment is positive, negative, or neutral. However, it's a bit more complicated than simple classification. Let's have a look at these comments for the movie. These are IMDb comments for the movie Scott Pilgrim vs. the World. We actually got a pretty high ranking on IMDb. The first comment is actually pretty simple to classify. I have indicated words like awesomeness, good, bad. It reminds us of classic text classification. However, sentiment analysis requires a decent amount of domain knowledge. For example, if I see this comment, achievement unlocked, one needs to know that this specific movie is about computer games, and that achievement locks is positive in the context of computer games. And these things are pretty hard to model. And the most difficult aspect of sentiment analysis is sarcasm. So sarcastic reviews are pretty fun to read, but they're pretty hard to analyze even for a human reader. Scott Pilgrim versus My Lamp. We all know that this is a negative review, but for a model to learn that, maybe tomorrow I'll have a movie about lamps that would have pretty positive implication, pretty positive association for this word. So sarcasm is actually the main issue in sentiment analysis. And the last supervised learning task, the one which will be the focus of this talk, is named entity recognition, or for short, NER. In classic named entity recognition, I have a clause or a short text snippet. I have a predefined set of entities, for example, person, organization, and location. And the model needs to find the entities within the text. For example, Jeff Meisters is a person, Cuba is a location. Okay? The NER task for today would be a little bit different. We'll try to predict the style of a text, whether it's bold, italics, underline, etc. But the same idea holds. Okay. If you haven't guessed so far, NLP and natural language understanding in general are pretty shitty at the moment. Has everyone heard about the Turing test? Great, so all of you. People decided that it's a bit too early to talk about the Turing test. We are nowhere near the amount of intelligence that required to actually fool a person. So the Vinograd scheme was invented. The Vinograd scheme can be thought of as a multi-choice questionnaire for Turing test, meaning I have this sentence. The trophy wouldn't fit in the suitcase because it is too big. And the question is, what is it? Possible answer would be the trophy, the suitcase, cannot know, both of them, whatever. Now, it's enough that I change one word here from big to small, and the answer completely changes. Meaning that the model has to know some kind of word knowledge that a trophy fits in a suitcase in order to figure out the correct answer. If that isn't hard enough, NLP is even harder in Hebrew. So now everyone talks about the Eurovision. So this is what Benjamin Netanyahu tweeted after Neta won the Eurovision. Neta, כפרה אמיתית ותרבה כבוד וכדומה. Neta, you're a real cow. That was the translation. Now, the people at Bing Translate know what they're doing. The problem is not with the algorithm, it's actually with the language. What happened here is that kapara was parsed as kepara, and the rest follows. So in Hebrew, tokenization, meaning taking a word and removing the prefixes and suffixes, splitting text into words, is not a solved problem. It's harder than English, and it causes these kind of artifacts. Another example, בוא נאכל בצל, or בוא נאכל בצל. We don't have the vowels. We don't have nikud. We actually cannot know from the text. So we need a lot more context in order to do things that are actually trivial in English or Spanish. By the way, as a rule of thumb, the more common a language, the more colonialists conquered lands and more foreigners speak a language, the easier it is to parse. Languages get simplified as foreigners speak it. So languages like English and Spanish are relatively easy to parse, while languages like, I don't know, Slovenian or Hebrew, for the matter of fact, are harder to parse. Okay, so this was our intro to NLP. Now we're going to talk about generating word vectors or token vectors from the textual content. So let's start with discussing what is a word. I can take my entire text and just split it by white space or punctuation, but what would I do with words like with web addresses? Obviously, www is not a valid word. What about phrases like bestseller, rest in peace? R is not a word, I is not a word. So tokenization might be an issue. In this workshop, we ignore it completely, but you can assume that smart tokenization is in place. Another potential issue are phrases. Phrases like New York, as is, in contrast with the UCLA, state of the art. The words by themselves don't convey the same meaning or information. Sometimes we want to unite them into a single word, meaning New York, as a single token. Also, the opposite holds. Words like overrated can be written as a single word. Maybe I want to split it into over and rated. You can think about languages like German or Finnish, in which words can be arbitrarily long. So splitting by white space is not always the right thing to do. Also, words like pancake, probably I wouldn't want to split pancake. And even more ancient words like manicure. Mano is hand in Spanish, cure is a cure. It wouldn't make much sense to split it. So also, things to consider. Another thing that's being done a lot of times to reduce the size of the vocabulary, also known as stemming. Stemming is essentially ignoring, removing the prefixes and suffixes from a word. So if I have a word like deserialization, I remove the D and the realization, and I get serial as a root word. It is not the same concept as root in Semitic languages like Hebrew, but it is still called a root word. Okay, so after we decided how we're going to tokenize and stem and define what a token or a word is, our next logical phase is to decide what set of words we actually care about. What is the valid vocabulary for us to consider? There are two techniques. One is actually to filter by frequency. So removing very common words like the, of, whereas in contracts because they don't convey information. And on the other hand of the spectrum, I might want to remove very rare words like people names or things that appear once or twice in the text, typos. There's another alternative, which is to use a dictionary. A word that doesn't appear in the dictionary, I don't care about. With Python, you can use NLTK, it's pretty straightforward. If I follow this process, for example, a sentence like this one, the lion is the biggest cat in the savannah, I might want to ignore all of the connector words, and then I get the words lion, biggest cat, savannah. I can get a sense of what's happening here. Sometimes useful, sometimes not. Okay, so assuming that I scanned my entire corpus, and this is my vocabulary. Amazon, Apple, Google. These are the only words that I care about. One-hot encoding is essentially this. I think it's easier just to see the slide. So each word vector would be a vector that has only one instance of non-zero values. The value here doesn't have to be 1. It could be any other value of significant, like the frequency of the word, the inverse frequency of the word, some kinds of property, whether the word was in a headline or styled in another way. But still, every word would have only one instance that is not 0. Therefore, the name one-hot encoding. If we follow this logic, we can also create a vector for the entire document, just by summing them, essentially. So here I have the word, the quick brown dog jumped over the lazy dog. So the word dog appeared twice. All of the other words appear once. And one needs to remember that the size of this vector is the size of the vocabulary. This same trick can also be applied to pairs of words, also known as bigrams. So we would have like the quick, how many times it appears, quick brown, and so on. Okay, so this was one-hot encoding, also known as the bag of words. Now we're going to talk about word embeddings, and to demonstrate this concept, we will use word2vec. Word2vec will not be the embedding that we would use in the workshop, but it's a good example. So, as humans, when we read this sentence, the capital of blank is blank. We know that the first blank is supposed to be a state or a country, and the second blank is a city, hopefully a capital city. So what word2vec tries to do is to encode a word according to its neighbors. So hopefully the vector for all of the countries will be the same, will be similar to one another, and the vector for all cities and capital cities would also be similar. This is like, if you know how word2vec actually works, so don't be angry with me. This is a simplification. Essentially, we try to predict the middle word, the center word, according to a certain window size. For example, 2 words before, 2 words after. And we get some kind of dense vector from the neural net. This is actually more accurate. And this is the result. Wonderful, right? I got a lot of random numbers here. So unlike bag of words or one-hot encoding, the vector itself doesn't mean much. So it's like 50 random numbers. But if I apply cosine similarity, I can find the vectors for the words that are appearing in similar context. For example, in legal contracts, I can replace customer with client, supplier, customers, etc., which is like super cool. Like all of those vectors are pretty much the same. No presentation on word2vec is complete without mentioning this example. So another cool property of word2vec is the arithmetic. If I take the vector of king, subtract the vector of man, and add a vector of woman, I get approximately the vector of queen, which is super cool. And also, if I take the vector of doctor, reduce the vector of man, and add the vector of women, I get nurse, by the way. So, just so you know. Okay, so now we covered word embeddings. Word2vec is only one instance. There are a lot of techniques to do word embeddings. We will not focus on that because actually it's not that important. But it will help us answer the question, how does words fit in a neural net? So, essentially, given a sentence or a list of tokens, each token corresponds with an index in a huge embedding matrix. So, I have a vector for you, I have some other vector for love, so another vector for I. I concatenate all of them and feed it to a neural net. This example is actually a classification example. The targets, as you see, is either positive or negative sentiment. And this example is so simple that you can implement it in like 6 lines, 7 lines. Pretty easy with Keras. Okay, so in this example, we covered what is called a fully connected neural network. All of the nodes or neurons are connected to each other. The next logical step is actually to convey some kind of structure. For example, if I'm trying to predict what is the style of the word must, this is a quote by Einstein, by the way. Life is like riding a bicycle. To keep your balance, you must keep moving. So I want to predict whether must is bold, italic, or normal. You would assume that the word must refers to some words around it. It's not likely that it refers to like life. So what CNN, convolutional neural networks, essentially do is they hard code it into the model. And every time we try to classify the word must, I only look at the words before and after it, assuming that the window size is 1. If the window size is 2, then I'm looking 2 words before and after my center word. reminds us a bit of Word2Vec. Word2Vec is also can be seen as a CNN. Okay, so here we have our neural net. As you can see, the word must, the prediction for the word must does not consider the input of moving. But when I try to predict the style of the word keep, then I move the sliding window one step down, and now I ignore the word you, and moving on for the entire string. So this was like the fastest way to describe what CNN does. And now we're going to talk about a very useful concept called RNN, recurrent neural network. So essentially, this is the first model that actually tries to maintain a state. What is going on behind the scenes? That I feed sequentially word after word, and there's internal mechanisms that is being learned. What do I need to remember or forget for each word? Assuming that I fed the entire sentence, some of the information is important and some is not, and hopefully this RNN model is going to update its state accordingly. So let's see how it happens in real life. I'm feeding the word you must keep your etc. to the same model again and again. I get some kind of internal state. I feed that internal state into a neural network. It could be fully connected or any other network, we don't really care. And this neural network is supposed to predict the class. In our case, whether it's bold, italic, etc., the styling. Okay, so this is a good point to stop and compare the two. So in theory, the RNN could remember dependencies from the beginning of the document. So in theory, RNN is supposed to be superior to CNNs that only account for a certain amount of words before and after. However, the sequential nature of the RNNs makes them harder to train, and it takes more time. So there's no clear winner, and sometimes the RNNs work better, sometimes CNNs. There's no, the jury is still out on this one. Okay, so far we covered the two models that apply to our problem. Now we're going to talk tachlis and talk about this workshop. Hopefully you all cloned the repo and you all have Python 3.6 on your computer and everything, and you all follow the instructions listed on the website. The data needs to be in the data folder, either in Google Drive or on your hard disk. Do not extract it. It's like, I think, at least 2 gigabytes or 12 gigabytes, I think. So don't. The code can read the data zipped. We very warmly recommend, we highly recommend to use Google Colab and not use your own machines unless you have GPUs, because it would be like 10 times faster. Okay, so in order to use Google Colab, upload it to Colab Notebooks / the name of the repo in your own Google Drive. Okay, we recommend not to download the data and upload it because it's a waste of time. You can just right-click the data and make a copy or create a copy or whatever, copy to my drive, and it will save you some time. After you clone the repo, upload it to Google Drive, and copy the data zip there, you can just run the notebooks by right-clicking it, open with, collaboratory. So, okay, so the question was which notebooks? We have 3 notebooks over there demonstrating the 2 models that we covered, CNN, RNN, and another one called bi-LSTM, meaning bidirectional RNN, in which we try to train from both sides. We read the sentence from the start to end and from the end to start, but this one uses PyTorch. Those of you who are familiar, go ahead. And after you're done training and tweaking your model, we have a leaderboard. After all, don't forget, this is a contest. Submission would be ranked according to line level accuracy. let's have a look at this hypothetical submission. So this is the right prediction. This is bold in bold, and this is underline in underline. And let's say that the submission was this is bold, and this is and this is correct. The line level accuracy is 50%, right? Because this is correct, and we don't care. If you made one mistake here, then we disqualify the entire sentence. So this is how the submissions are ranked. And we have a leaderboard at this link, which will update live. As you post a submission, you will see how you rank against each other. The winners will get, Leo? So what he said, and at 9 p.m. we'll be announcing the winners. One last thing, if you have any issues, any questions, we have a pretty large team of mentors. Mentors, please raise your hand. Any one of them does NLP for a living and should be able to answer any query that you might have. And one last note, we try to support local startups here. We have Dean and Guy. Dean and Guy created a notebook demonstrating the use of this use case in their system, Degs Hub. I pronounced it correctly? Yeah. They will also help you both with the problem, and it will give them a chance to see how their systems stack up. So, let's get hacking.